Guys, in this video, I would like to explain a simple linear regression analysis using R Studio. Maybe you know that what is meant by regression analysis. Regression is the relationship between two variables in which we say one variable is dependent variable and the other variable is independent variable. This means one variable depends on another variable. And there is a difference between the correlation and regression analysis, which I explained in my video. And the link to that video is mentioned in the description of this video. So correlation is the interdependence between two variables. And regression is the dependence of one variable on one or more other variables. So in this today video, we would like to talk about simple linear regression analysis. That's mean we will talk about single dependent variable and single independent variable. This means that there will be one variable that will be dependent and depend on a single independent variable, which is also called covariate regressor, etc. So before going to R, I would like to talk about simple linear regression analysis briefly like this. You can see these are some of the steps we need to take required data. If you are talking about simple linear regression analysis, this means that I already talked about this. You have two variables. One is independent and the other is independent. One is independent and the other is dependent. So we need to have data on these two variables. That's required data. Identify the suitable model. So you can identify by plotting the data. Normally we are using simple linear regression model, but if the data has some other patterns, then maybe you can use other models. Estimate the parameter. This is the important step. You need to estimate the parameter of the model, because this will give you information about the relationship between the two variables. So estimate the parameter. You can use different method like maximum likelihood method and least square method is usually used in regression analysis, but it's depend on the assumptions of the model as well. Diagnostic checking of the fitted model. In the model, you need to check some assumption. If the assumption are violated, then you need to transform the data. You need to have some transformation to meet the assumptions of the linear regression model. And once you establish a model, you estimate the parameter and you check. And if the model passes the diagnostic checking, you can predict the future behavior based on the values of the independent variable. We will not talk about prediction in this video. We will talk about simply only 4 steps, but not the prediction. With the prediction we will do in another video. So this is all about regression. You can see from the literature how we can write a regression model, and you can also go for the derivation of the parameter if you are interested. I will do this in some other video, but not today. So let's go to R now, that how we can do these steps in R. Okay, so this is my script, and I'm using online data, which is attached with the R, and you can have your own data. It's no problem. You need to data and the two variable for this model which we are talking about today. So you need two variable. One is dependent variable and other is independent variable. So whatever you can read from CSV file or whatever. Okay, so my data is from empty cars. If you want to know about empty cars, you can just write here. The screen is by Control L and write empty cars bracket. Okay, no problem. I already opened this. So empty cars Nice. Okay, so you don't need to do this. Is just for the function when you want to function. So this is, you can see the data by looking like this empty question mark and then the name of the data, and you will see this detail. I will not talk about the detail into the video because this is now video, so you can go and you can just click on like this command and see the details. It's simple in English. You can. And I will talk about the two variable which I'm using only. And you can see this empty cost data is from data sets. So this is the package. This is the data set from this. So empty cost data, you can just load the data set just using this command and then hit empty cars. View first few values of the empty cars. So you can see, just click again. So you will see the detail. Yeah, like this, because the space is limited. So some column went down. So this is like, we'll see like this data. And we are talking about two variables. One is MPG and the other is HP. HP horsepower and MPG mean miles per gallon. Okay, this is from the United States unit or something like this. So miles per gallon, and this is horsepower. So in this case, we'll try to find the relationship, and you should know which variable is dependent and which variable is independent. This is very important in regression analysis. So now you need to fit the model. So the model formula is look like this. This is LM, and this is simple linear. This is for simple linear regression. This function, if you are using, then you can use other function. If you are using generalized linear model or something like this. So LM and then the dependent variable, and then this distributed are this this symbols, and then the independent variable, and then you can write data. Data is empty cars, which is already mentioned. So data. So this function will estimate the model. Here MPG is dependent variable, HP horsepower is independent variable, and MPG is dependent variable. And this model is stored. This the estimated model is stored in model. This is you just mentioned this here, assign so the model, the estimated model is now in this. Just click on this. So now the model is estimated. You can estimate intercept and slope and their p-values and significance, etc. Just click on this summary model, and you will see details of the model. So this is the formula, and these are the residuals. We will talk about the residual later, so we don't need to talk about this now, but there are some statistics mentioned about the residuals in the coefficient. That is the important thing for us is the coefficient at the moment. This is intercept. This is slope. So you can see MPG is a dependent variable. So this is, I want to show you again. So this is, this is MPG is here, which is not shown. There's no plot. That's better to plot it. So you can plot like this. Explain this later. So you can see MPG mile per gallon is dependent variable, and then horsepower is independent variable. And you can see the relationship is going down. The horsepower, mean the power of the engine is increasing. The mile per gallon is also okay. Miles per gallon. The horsepower increasing, miles per gallon decreasing. When you increase this variable is decreasing. The relationship is declining. When the horsepower is 50, the miles per gallon, the mileage, we can see simply the mileage is higher. In this horsepower is increasing, miles per gallon decreasing, is coming down here. This is here, but it is here. It is here. The minimum is here. That's depend on the car we are using, which new or old or whatever. There's a lot of things, but we are talking about this two variable in today's video. So this means this is like you said, this is y, and this 30 is alpha. So to show that again, this one, this is the model, and this is my graph. So this means that this variable is y is equal to alpha, which is 30.098 or 0.99 plus minus 0.068 into x, which is horsepower. So this is the coefficient of this variable. It means that this variable has negative impact on the mile per gallon. So the coefficient is negative and the magnitude is not strong, but it is negative. So this means that one unit change in this can cause this effect on this variable. So this is the change, per unit change in this variable, per unit change in this variable as represented by this one minus this one. So this is the intercept, the alpha, and this is the beta coefficient of this variable. So you can see there is an inverse relationship, negative relationship. The horsepower, increasing the horsepower, decreasing the miles per gallon. This is obvious. You can see simple in daily life. And okay, so this was just plotting. You can write the variable. This is empty cars, and when you write the other sign, you can extract this variable. So this is one variable, horsepower, and this is mpg is another variable. So the data set and dollar sign, that variable. This is the linear, simple linear regression example, and then you can write x-axis this label, y-axis this label. You can change the color, no problem, whatever you want. You can write red. So this will be obviously red. So that's not important, but if you want, of course you can do it. No issue. Yeah, like this. Okay. And okay, now the important thing is, okay, you draw this line, you draw this plot. Okay, I will write this blue color because there is a red color line. So this is now the the data, and now the fitted model, which is a line, the line, the model, which is I fitted the line, the data. That will be with the red line. Just run this, and you will see now. So this is that line. The alpha. I can now explain this. Alpha is 30.099. So alpha is here. This is not 30.0. Okay. So this is something here. Not 30.009 here, but and this is the slope line. I think I need to again. This is where it is. This oh yes. So the slope of this line, the rate of declining this line is mentioned by this. And the important thing is, sorry, the important thing is this shows the significance, the p-value. So both the parameters, the alpha and the beta, both are highly significant. You can see significant and significant. So both variables are highly significant. So this means that there is a significantly impacting the horsepower, significantly impacting the mile per gallon. Okay, this is all about identifying data, required data, and identification of the model and estimation of the parameter. Now the important thing is we need to check the assumptions. The assumption is we need to talk about all the way with the residuals now of the model, which is the difference between the actual values and the predicted values. So just run this. So we calculated residual. This is now in this command, this function calculate residual, and this is the model which we fit. You already fitted. So the residual is not here. So just plot the residual. Oh, okay. It's not the plot. It is the normality test, but you can plot the residual. RES type L LWV line width equal to COL equal to red. So you can see this the residual. The mean value is just looking like here, but anyway, this is a rough plot. We need to check about important thing, that is to test Shapiro-Wilk test. One this is for the normality test. So just run this test. You will have the result, but I think we don't know what is meant by this test. So we need to just click. We need to click Google it, Shapiro-Wilk test. The null hypothesis in Shapiro-Wilk test, because this is important. If we don't know about the null hypothesis, how you can decide Shapiro-Wilk test. Okay, so further in the alternative hypothesis and choose a degree of confidence for Shapiro-Wilk test. The hypothesis that the sample come from normal population. Remember, this is very important because I will tell you why. The data come from normal distribution. Okay, now this is the Shapiro-Wilk test, and the p-value is the word W, that is statistic, and this is the p-value. The p-value is 0.025. So that's look like we reject the null hypothesis, and the data is not normally distributed in this case. Yeah, if the p-value, because if we are talking about at 0 and 0.05, I mean that 5% level of significance, and this is not normally distributed. So in this case, then we will need some transformation. And the other test you can use, that is, okay, this is Anderson-Darling test, AD.test. For this, you need this library. So I'll just try this. You can use 2-3 tests. In this case, just check what is the null hypothesis. I think null hypothesis might be the same as we have in the Shapiro-Wilk test. Okay, the data are normally distributed. So the same thing here also, it means that the data are normally distributed. And you can see this is the test statistic, and the p-value is 0.03, which is less than 0.05. So at 5% level of significance, we reject the null hypothesis and conclude that the data is not normally distributed. The residual are not normally distributed, which is the assumption of the regression analysis. You cannot do prediction with this model. You can do, but there will be a lot of problem with the prediction, because you need to fulfill these assumptions. You need to apply some transformation. And this was something statistically to test. You can test whether it is, there are other tests as well. You can do zero test and other tests. But I think these two are enough, which confirm that the data is not normally distributed. You can use QQ plot, those test one the numerical ways, and now you can use graphical ways as well to see whether the data look like normally distributed or not. So this is now QQ normal plot. You can draw a line. You can see this is, yes, particularly at the extreme, the value is far away from the line. This data is up to some extent okay until here, but these values create problems. What happens due to this? These values, the data is not look like normally distributed. Using both tests, and that's Shapiro-Wilk test and Anderson-Darling test. You can plot the residual by using this command and to see what is how the residual, the plot, the histogram look like. This is the histogram, and yes, these are the values which are far away. The higher extreme values is the lower, this is the higher extreme values. See, these are the values which are far away from the other values, and this create problem. And due to these values, it look like not normal. In the next video, I will exclude these values. This video is going lengthy, so I just want to explain how this regression works. And what you need to do if the data is not normally distributed, you need transformation. You can use log transformation, you can use inverse transformation, you can use square root transformation, you can use Cox transformation to make your data normally distributed to fulfill the assumption. Anyway, it's not the purpose of this video. I will talk about this in some other video, not in this. And now you can draw the curve, the density curve to see. Yeah, so this is the problem. This can be a bit normally distributed if this like this. This is not. This can be a mixture distribution, can be a normal distribution mixture, but I don't know if there are other tests for there. So we are not talking about their complex problem now. We will talk about mixture distribution sometime later in the other video. So this look like graphically we saw that the data does not look like normally distributed, like you can see with the QQ norm as well. Yeah, these are the values which is outside, which are the extreme. And with the test as well, you well can Anderson-Darling test also show the data is not normally distributed. So we need some transformation to make it normal. Okay, so in today's video we learn about what data we required for a simple regression analysis, identify the suitable model, estimate the parameter, and diagnostic checking of the fitted model. So we have a problem. The data is not normally distributed. So we will need some transformation, and we will talk about transformation later, which make the data normally distributed, and then you can do prediction. About prediction, we will talk about this in some other video. So thank you very much for today, and see you in the next video.